Good morning.
What is that? Good morning.
Who called it?
All right, well, let's see. Anybody in Joseph City yet? No. All right, we've got Holbrook. How about Winslow? Anybody absent in Winslow?
Shandon's absent. Brooke and Taylor are gonna go to a softball game right now. So
Okay. Yeah, I think Brooke emailed me on that, so thank you. All right, is Caden there? Toby?
I think so.
Okay. All right, well, let me know. I'm sure I'll notice, but
Okay, I saw him this morning. I think he's just late.
okay. All right. Okay, so the plan for today is we have a short section in 9.5. So we're going to do that and finish up chapter 9. And then we'll start in on the last chapter that we're going to cover, which is chapter 11. You might remember we actually kind of did chapter 10 last semester. So that's why we're jumping over that. So, but any questions, comments, concerns before we get started?
could you remind me real quick, like which way a parabola opens?
Okay, if the x is squared, then it opens up or down. And if the y is squared, it opens left or right.
No, I mean like, how do you determine if it opens left or if it opens right?
Okay,
Is it if it's just positive or negative?
if when you calculate the p is the directed distance from the vertex to the focus. And the focus is always on the inside of the parabola. So if you move over a positive 2, then it's going to open to the right if it's a sideways parabola. If the p is negative, then it'll open to the left. Now, if it's a vertical parabola, if the p is positive, it opens up, and if the p is negative, it opens down.
Okay, thank you.
All right, you bet. Anything else? Any other questions? Okay, well,
Caden's here.
I don't have 9.4 now.
Oh, okay. All right, thanks. Yeah, I did also send out the 11.1 because I think we are going to get into that a little bit. I would at least like to introduce it, and you'll see why when we get there. But anyway, all right. Okay, so let's share. Okay, and change the camera. Okay. All right, so 9.5. So, like I mentioned, this is kind of a short section again. When we get to chapter 11, then the sections are a little bit longer again. Okay, so this section kind of mixes what we did last chapter with polar coordinates with the stuff that we're doing in this chapter with conic sections. So it helps to remember some of the stuff in chapter 8 on polar form, as well as the conic sections. So the polar form of conic sections. Now, those of you that take calculus, go on to take calculus. In calculus 3, we actually go through and do this very same section again, almost identical to this right here. So anyway, it's a good review. So we'll use the polar form to identify the conic, and then determine the directrix and eccentricity, and then we'll also construct a polar equation given information about it. Okay. All right. So this is the screen with a lot of the notes on it. Okay. But it says let dPF be the distance between any point P and the focus. So that's why it's dPF. So from the point to the focus. And dPL be the distance between a point and the directrix L. Okay. So the distance, so the ratio of those two distances. So the distance to the focus divided by the difference of the directrix, we're going to define that as E. Now that's slightly different. When we were studying the ellipse, we said it was C divided by A. Well, that's actually what those were with an ellipse. But this is a more general definition to include all of the conic sections. So the distance from the point to the focus divided by the distance from the point to the directrix, that is E, or the eccentricity. All right, so
So what does eccentricity mean exactly?
okay, so when we talked about the ellipse, the eccentricity was kind of the ovalness. All right, like if it was more round or if it was narrow or whatever. And so that's with the ellipse. Now with the other conic sections, it just refers to like the general shape, like how flat it is or how wide it is, that kind of stuff. Like how wide the parabola is going to be, or if it's narrow. Same with the hyperbola. Now, so see, we never really talked about the fact that all of these have a directrix. See, we never, when we studied the ellipse, we talked about the focus, but we never talked about the fact that it had a directrix too, or that a hyperbola has a directrix. And we're not really going to graph it or whatever, but you do need to know that all the conic sections have a focus and a directrix. Okay? And so depending on where that line is, where the focus and the directrix are, it changes the shape of them. And so that's the eccentricity. So when you calculate the eccentricity, if you actually, the conic is an ellipse, if the eccentricity is between 0 and 1. Now, actually, I would probably, this is just kind of how the book has it organized, but I would probably add another one. What if E is actually equal to 0? Does anybody remember when we were studying ellipses, I told you what would happen if the eccentricity was 0. Anybody remember that? What kind of shape it would have?
Would it just be like a line?
No, that's if it's actually equal to, the closer you get to 1, it smashes the ellipse and it actually becomes a parabola.
So it's a circle.
It's a circle. So the conic is a circle if E is equal to 0. So I'm just adding that on there. But from this section, they're saying, okay, if between 0 and 1 you get an ellipse, if E is equal to 1 exactly, you get a parabola. And then if E is greater than 1, you get a hyperbola. So what I'm going to do is show you how, if you have in polar form, it's great because usually you can either look at it and tell, or just do a simple little like pre-algebra, solve a pre-algebra equation to get it. Okay, so the math here, once you learn the rules, the math here is actually going to be pretty easy. Okay, let's see, we don't need that. Okay. Okay. All right. So now this is the other page of notes here. So the polar form of conic sections. So I've got the first two lines, and you actually might want to do like I did and kind of separate them just to help you kind of organize, because there's a lot of information here. So there's basically four types of polar forms for the different conic sections. All right? So let's just kind of contrast and compare all four of them at the same time. So they all are solved for r equals, okay? And then they're all fractions, and they all have ed in the numerator, okay? E times d. Now, so E times d, E is the eccentricity, and d is the directrix, the distance to the directrix. So the numerator is E times d in all four of them. All right, then all four of them in the denominator have a 1 in the denominator. All right, now, and then they have plus or minus, and then E times either sine or cosine. All right, now, again, the E is the eccentricity. And what's the difference? If you have a cosine down here, then that makes your directrix vertical. If you have a sine in the equation, that makes your directrix horizontal. In both cases, what the equation is, whether it's x equals d or x equals negative d, that plus or minus depends on the sign in front of the e. That determines whether it's going to be a positive or negative value. Okay. Anybody need more time on that? Okay. All right. So what we'll have a problem like this, where we'll be given a polar equation, and then we'll be asked one or more of the following. So we'll want to identify the conic, find the equation of the directrix, and then sometimes we'll also be asked to find E and D. Okay? So those are the things that you need to be able to do. All right? So first of all, to identify the conic, what we want to do is put it in standard form. So actually, let me write that as a fourth skill that we need to be able to do, is put in standard form. Now you might say, wait, that looks like those other ones that I just put up there. But just kind of going back a slide or two, all of these had a 1 down here in the bottom. They all have to have a 1. So before you start doing anything, where this 5 is, I need to make it a 1. So how am I going to make it a 1?
Could you like simplify? Because like the 15 goes into the 5, or the 5 goes
So,
into the... Did you do that?
could I cancel the 15 and the 5? Making that a 1
Yeah.
there?
Yeah. No.
Nope. Okay. See, like if I had see a fraction like that. Well, let's make it a 2 here. Could I cancel the 15 with the 5? No, you can only cancel factors. And so 5 is not a factor here. So you cannot cancel it. Okay? But that's a good guess. It's a good thought. But no, you can't cancel the 15 and the 5. So how am I going to make the 5 a 1? So I need some algebra experts here. Algebraically, what do I do?
Multiply by 5.
If I multiply by 5, then this is going to be 75, and this will be 25, and that'll be 15. So, but you're actually close. What? Go ahead.
Divide the whole thing by 5?
Divide everything by 5. That's it. That's it. So you're going to divide 15 by 5, the 5 by 5, and the negative 3 cosine theta by 5. So everything gets divided by 5. Okay? And so then I'll end up with 15 divided by 5 is 3. 5 divided by 5 is 1 minus 3/5 cosine theta. So that's the standard formula. Okay? All right, now, what is E? Any guesses?
3/5.
3/5. And how'd you get that?
Because the E is in front of the cosine.
Because the E is in front of the trig function here, sine or cosine. So the E is 3/5. All right, now, what type? So if E is 3/5, what type of conic section is it?
Ellipse.
It's an ellipse because 3/5 is between 0 and 1. Okay, so it's an ellipse. Very good. Okay, next. To find D? Now, usually you can just look at it and find E. All right, now to find D, because we've used that to find the equation of the directrix. So to find D, then what we do is we use the top, once we've put it in standard form, and say 3 is equal to E times D. Because the numerator is ed, E times D. So ed is equal to 3. Well, now if E is 3/5, you substitute that in for E, and then you solve that for D by multiplying by 5/3. And so then we'll get D is equal to 5. Okay? Is everybody cool so far? Okay, so now to find the equation of the directrix, we actually have to put together 3 pieces of information. Okay? Now, it's all 3 of them are just things that we can look at, but we have to put together the 3 pieces of information. Okay? First of all, to figure out if if the directrix is vertical and has an equation of x equals, or if the directrix is horizontal and has an equation y equals, we look at the trig function. Okay, if it's cosine, then what? Is it x equals or y equals?
X equals.
Okay, so the equation of the directrix then is x equals. So that's piece of information 1. Okay, the second piece of information is the sign in front of the E. So negative. So it's x equals negative, and then the last piece of information is the d. So x equals -5 is the equation of the directrix. So we have to have all three of those things put together. Okay? All right. All right, any questions? Okay, so for practice 1, I want you to, I want you to do all of that. I want you to identify the conic, find the equation. Well, I guess that's the same, in standard form. And then we're going to find the directrix and find E and D. So I want you to do all of that for practice 1. Okay, so Junior, what is the equation in standard form?
R equals 2/3 over 1 plus 5/3 sine theta.
Excellent. Any questions? All right, so Jordan, what is E?
5/3, 5/3.
That is correct. Very good. All right. Diana, what's the conic section?
Hyperbola.
Okay. Oh. Hyperbola. Good. All right. And all right, so Jordan, what's D?
It's y equals 2/5.
Or, no, just D. That's the next question. is what's
Oh.
the equation of the directrix.
Oh,
So-
okay.
So what's D?
Just 2/5.
2/5.
Yeah.
Oh, where did I put it? Okay, so D is 2/5. And so Jordan, go ahead and tell us what's the equation of the directrix then?
Y equals 2/5.
Y equals 2/5. All right, very good, everyone. Any questions? All right, super. Okay. So in this scenario, D is the distance between the focus and the directrix. Okay. So this says construct a polar equation left opening parabola with a focus at the origin and the directrix 2 units from the focus. Okay? So in this case, what you have to do is figure out what the E and the D would be. Okay? All right, so here, if we have a parabola, we know that E is what?
It's 1.
It's 1. So if we have a parabola, we know that E is 1. Okay, and so if the focus is at the origin and the directrix is 2 units from the focus over here, then what is D?
2.
It would be 2. All right? So now when we're trying to come up with the equation, remember in the numerator, so it's R equals, and then the numerator is ed, E times D. All right? So we put 1 times 2 in the numerator. All right? Then we're going to have 1. All right? Now, okay, so coming back the other way, what's the equation of this vertical line right here? What would be the equation of the directrix as I've graphed it? So it's a vertical line, so it's x equals. So in the equation, are we going to put, oh, and then it's plus 2. So I'm going to have a plus, and then if I have a vertical directrix, do I use sine or cosine?
Cosine theta.
Cosine. So it's, E times 1 plus E, 1 times cosine theta. And so then if I just want to simplify that, then the equation would be 2 over 1 plus cosine theta.
So if you did actually have like the angle, would it just like rotate the?
Well,
Conic?
what it is the angle, you remember in polar form, to get the whole polar equation, see the angle is like your variable. So it's like when you graph a line and it's y equals 2x. If you plugged in a specific x, you would get a point. But when we keep x in general, then that's how you get a line. So if x is 1 and whatever. So it's the same thing. If you plugged in a specific angle, you would just get 1 point. But in general, it generates the whole polar curve. Okay? All right, so, but that's a great question. But so we keep it general so that like if the angle is 20 degrees, then you get 1 R. If theta is 45 degrees, you get another R. And so then you plot those points. Okay? All right, so see if you can do practice 2. All right, so Tiana, what's E?
1.
1. Okay, because it's a parabola. All right, Cameron, what type of conic section is it? Oh, no, we already told us parabola. What's D?
3.
3. All right, so Ellie, what's the equation?
So R equals 3 over 1 minus cosine theta.
3 over 1 minus cosine theta. Very good. All right. Is that all? Yep, that's it. Now, what's the? Can anyone tell me what's the equation of the directrix? It didn't ask you to find that, but can
X
anyone tell me?
equals -3.
X equals -3. See, it's because it's on this side of the origin, so it'll be a vertical line because it's cosine. X equals -3. All right. Any questions on that? So that's it.
So the positive or negative is based off of the directrix?
Yes.
Okay.
Yep. Yep. So good. Okay. So that's it for 9.5. And that's it for chapter 9. So you can be looking for, so I'll put it out the quiz and the test for chapter 9. Okay. All right. Now, what I don't want to really get into too deep for chapter 11, but there's a reason why I want to start it today, and hopefully you'll see why that as we go. All right. Chapter 11 is on sequences and series, and you might have done this a little bit in Algebra 2. Okay. As a matter of fact, you might remember doing like combinations and permutations and that kind of stuff. So usually the student, a lot of this chapter is going to be a review of that. So there's not, I mean, we'll go into more detail, but I think you'll find that this chapter might be the easiest chapter this semester. Okay, so we'll see. All right, so when we talk about sequences and series, one of the biggest ideas in understanding this is just understanding the idea of a pattern. Okay, and they say that patterns are crucial to understanding mathematics in general. Okay, so like here, this is a sequence of numbers that forms a pattern. So can anyone tell me what would be the next number in the sequence?
15.
15? That's right. Okay. Now, sometimes there's more than one way to do a pattern. And so you might have thought of something else. If you can demonstrate that your pattern works, then it has to be a right answer. Okay. But this 15 is the answer most students give, because here, the difference here is 2, 3, 4, 5. Okay. Now, there's other patterns that are like geometric. So you could say the pattern of 3 dots forms a triangle, pattern of 6 dots, 10 dots, 15 dots. So this same pattern can be shown geometrically. Now, as a matter of fact, in ancient Greece, they called these numbers triangular numbers because they could make triangles out of the points. Okay, so it's the same idea. All right, now this is a pattern. Anybody know what this pattern is?
Is it Morse code?
That's a great answer. Great answer. I really don't even know enough about Morse code to know the pattern, but this isn't it. But there are, if you did know Morse code, maybe somebody out there can do a pattern with that. But what this is this is actually Mayan mathematics. Okay, how the ancient Mayans wrote their mathematics. Now, to me, this is fascinating because the Mayans were actually more accurate in their mathematics than any other people in the world at that time. Okay, but this is how they counted: 1, 2, 3, 4, and then 5 was a line. Okay, then after 5, then they would. This was 6, so this was a 5 and a 1. Okay. The other thing that's fascinating about the Mayans mathematics and their patterns is that they had a base 20 system instead of a base 10 system. Anybody want to guess why? They had a base 20 system? Well, see, unlike the Arabs and the Europeans, the Mayans typically didn't wear shoes. And so they could count on their fingers and their toes. And so they could go up to 20, before they had to have, in our system, we have, the ones column and then the tens and then the hundreds. Well, the Mayans had 20s, and then the 2020s would be 400. And so they had a base 20 system. So they could actually represent larger numbers on a much more compact scale too. So another advantage of the Mayan. But anyway, it's all about patterns. All right. Now, so sometimes you can use letters to represent other things. They could represent words or whatever. So this is a pattern. Anybody know what this pattern is? Just looking at it? Okay. Well, this pattern is the states along Route 66, starting with Illinois and ending up, so here's New Mexico, Arizona. So what would come last? California, because this is going from east to west. Okay. But this is a pretty specific, this requires some specific knowledge, not only of history, but geography. But it's a pretty good pattern. But I would suspect that not many of you would figure that one out. Okay. All right. How about this one? Anybody have an idea of what this pattern would be?
Aren't they elements?
The elements. That's right. Anybody know what particular elements?
Helium.
Come next. What?
Helium, nitrogen, argon. I don't know what the KR is.
Argon,
Krypton,
krypton,
Xenon.
Xenon. Anybody? What comes next?
I don't know, less.
Radon. This is specifically the first column in the periodic table, what's called the noble gases. Okay, so a little science there. Okay, so now as we put up different sequences, there's some of them that sort of have an end and other ones that go on forever. A sequence that goes on forever is an infinite sequence. And so when you see the ... at the end, it means it goes on forever. The A sub 1, the A sub 2, A sub 3, A sub 4, these are the terms of the sequence. Okay? And so if it ends, then it's called a finite sequence. So finite, infinite. So if to find the first three terms of a sequence, for example, if we have an expression or a formula for it, then you just plug in 1, 2, and 3 for n, and that would give you the first three terms. Okay. So here, this is a finite sequence because even though it has a ... it ends at 10. So this is just, say, a way of skipping. Okay? So again, this is a finite sequence because the dots are in the middle. This is an infinite sequence because the dots are at the end. Okay? All right, so anybody want to guess what are the last two letters of this sequence? Okay, I'll give you a hint. The hint is history. And that each of those letters represents a name. All right, so Ellie, you look like you're having an epiphany there. What's the last two letters?
It's gonna be O and T.
It will be O and T for Obama and Trump. So these are the U.S. presidents starting at Washington. Okay, excellent, excellent. So if we have a formula for a sequence of numbers, and we want to find the first 5 terms of that sequence, then we plug in 1, and we work it out and get 1, and then we plug in 2, and we work it out and get 4, and then we plug in 3, and we work it out and get 7, and then we might start seeing a pattern to say, well, it goes up by 3 each time. So maybe the 4th term, a sub 4, would be 10. And then a sub 5 would be 13. And so I don't have to calculate it each time if I start seeing the pattern. Okay? All right, so do practice 1A, where you find the first 5 terms of that sequence. And I did, yeah, it looks like everybody got it. Good. All right, Jordan, what do you have?
I have 3, 5, 7, 9, and 11.
3, 5, 7, 9, and 11. Very good. Any questions on that? See, I mean, really and truly, compared to some of the math we've been doing, is this not easy? Okay. I mean, anyway. All right. Okay, now, so -1 in parentheses raised to the n is what I call the alternator. Because what it does is, as you start putting it in a sequence, it alternates the sign, positive and negative, or at least it for that. Because -1 to the first power is -1. -1 to the second power is 1. -1 to the third power is -1. So this term is going to alternate between 1 and -1. All right, so this is 5. Find the first 5 terms defined by this. So here we start with the first term. So that would be -1 plus 1 over 2. So 0 divided by 2 is 0. All right, then the b sub 2. So that would be -1 squared plus 1. So 1 plus 1 over 2, 2 over 2 is 1. Well, then I do b sub 3, and I think, well, it's going to alternate back to 0. And then 1, and then 0. So, again, just seeing the pattern. All right, so see if you can see the pattern there in practice 1B. All right, Dominic, when you've got it. Is Dominic there?
I got the first three.
Okay.
1, 3 over 2, and 1 over 3.
Okay. Yeah, you're a little cut off there from the camera. I wasn't quite sure. All right. So you had 1, and then what was the next one?
3 over 2.
And then what was the next one?
1 over 3. And then
And then how about the next one? Yeah, see what's happening here is it's just the numerator that's alternating. So the numerator is alternating between 1 and 3, but the denominator is just going up, counting up. So we could just look at the pattern and say the next numerator is going to be 3, and then the next denominator is going to be 4. Do you see that? So even without plugging in, I can see the pattern. So without looking at the formula here, just following the pattern, what would be the next number?
3 over 4.
What is it?
3 over 4.
And then after 3 over 4?
1/5.
1/5. Okay, good. Okay. So this is all about patterns. Whoops. Whoa. Okay. All right, we're going to come back to that. Okay, so what I want you to do for Monday is I want you to come up with a pattern that you're going to try to stump me or stump the class. Okay, now I'm going to give you some examples of some patterns like we've done before. So they have to be ones that within everybody's knowledge. Okay, so like for example, let's do some and so this one. So what would be the next
W.
W? And because this is just the days of the week, okay? So yeah, that's great, but that's too easy. Okay? All right. So how about this? This one's actually a little bit better. Anybody have an idea what would come next? I'll give you a hint. If you're a senior, you should know.
It's
Okay,
a T.
some of that I'll give you more time, but we're running close.
It's a T.
It's a T. Kindergarten, first, second, third, fourth, fifth. Okay, so 11th, 12th. All right, good. Okay. How about this one? Similarly, this is just counting. 1, 2, 3, 4. So F would be next. 5. All right, how about this one? Now, come ready with a hint too. So the hint for this one is you have a better chance of this one if you go to Sunday school. So what goes in the blank?
It's a D.
It's a D.